topic for today is going to be on continuation of our topic we started last time. Last time we talked about metals. For majority of the lecture, we dwelt on reactivity and stability. So today now, we are going to look at the occurrence and preparation of these metals, especially the group 1, group 2, and group 3. Although it's not going to be like we are taking every element of the group, just try to take some representative among them, and don't forget that each group has similar properties for the element involved. So if you take one of the elements in a particular group, then we use it to generalize for that whole group. So at the end of today's class, it is expected that students understand the natural sources. We should be able to identify the natural sources of these representative metals. Then we have to be able to describe the various methods that is used to prepare these elements from their sources. This is predictable. Once again, we are familiar with it. So our aim of today's class now is going to be like we are focusing on group 1, group 2, and aluminium in group 3. Then we take 1 or 2 from the transition metals. Although we still talked about transition metals in detail, but we just want to take 1 or 2 of the most common elements, transition metals. Don't forget the last time I said the reactivity of elements is a particular indicator of how they can be prepared. I said even the occurrence of elements in the earth crust is a function of, is determined by the reactivity. Like sodium now. So sodium is a very, very highly reactive metal. That is why we can't find it in pure form. So it has to be in ores, in compounds of sodium in the earth crust. So if you need sodium from the compound, we have to do some preparatory methods and purification methods. Don't forget I said also, because gold is highly unreactive, so it is easy for gold and silver to be digged from the earth crust and just clean it. Then that is our gold. This because it's highly unreactive. So now, what is called representative element? These are just elements in S and P block on the periodic table. Don't forget I said during our lectures on periodic table, we said the shell, the orbital to which the valence electron of a particular element belongs, that is the block to which the element belongs. If you have valence electron in the s orbital, so that element belongs to the s group. If you have it in p orbital, it belongs to the p group. So now when we say representative element, those are the elements in the s and p block. These are the elements that have completely or partially filled s or p orbitals. So example is group 1 up to group 0 or group 8, as the case may be, depending on the classification you are considering. So those metals in these groups are called representative metals. An example, lithium, that is in group 1, rhodium in group 1, magnesium in group 2, calcium in group 2, then aluminium in group 3. Those are the commonest representative metals that we have. So now, occurrence. How do they occur in nature? We do not always find this element in freely like that in nature, as I've said, because of their high reactivity. How do we find them? It is from their compounds. Their compounds are very, very abundant. Example is these minerals of lithium that is that occurs in the form of silicate and phosphate. the same thing, sodium, potassium, they are formed from the evaporation of sea water. So when you have sea water, you know, don't forget sea water contains some soft salt inside. So the evaporation of sea water has some silicate of salt, silicate of potassium, some sulfate of potassium, some sulfate of sodium. Those are the conditions where we can find all these elements. Another one is all these alkaline elements, those group 2 elements that occur as silicate, some as carbonate, some as sulfate. So out of the elements of the group 2, I mean the alkaline earth metals, beryllium is the only one that doesn't have sulfate, doesn't have carbonate, doesn't have silicate. Instead, it occurs what is called a mineral berry. Now that is the complex formula of this. So that is the only way beryllium is found in the earth crust in nature. So the main source of aluminium is bauxite. Everybody know what is called bauxite. That is aluminium, the oxide, combination of oxide, hydroxide of aluminium. When we get there, we're going to talk more about bauxite. Again, aluminium occurs in clay. There are many types of clay. So aluminium occurs in them, although the quantities are not the same. The main ore of tin is called cassiterite, that is zinc oxide. Cassiterite. So just try to get the name cassiterite. Lead and thallium ores are always in sulfide or weathering of product of weathering of sulfide. So it can be in sulfide form, maybe sulfided lead, sulfided thallium, or the product from the weathering of other sulfide. So that's when you say lead and thallium. Then the representative element occurs as impurities in zinc and aluminium ores, I mean other elements. This does not mean these are just the little compounds of all these representative elements. There are many common, but the one we have talked about now, they are the majority. They are the majority. So now let's now go to preparation of sodium. The only way to prepare sodium, because sodium is a very, very reactive element, the only way to prepare it is electrolysis of molten sodium chloride, that is called brine, molten sodium chloride. So when you set your electrolytic cell, that is in this case is Downs cell, Downs without apostrophe, Downs. So we set the electrolysis like that. So the electrolyte now is the molten sodium chloride. Don't forget, molten sodium chloride is different from dilute or concentrated sodium chloride. This is molten. When you have solid sodium chloride, then you heat it until it becomes melted. So there's no water inside. So when you have molten sodium chloride as your electrolyte and you have inert electrode, you can use carbon as anode and carbon as cathode. So don't forget what we talked about in electrolysis. We are going to have dissociation of this compound into ions. So we have sodium ions and potassium ion. So now there's going to be movement towards the electrode. So the positive one moves to the cathode, the negative one moves to the anode. I mean sodium ion moves to the cathode, then chloride ion moves to the anode. In the cathode there is going to be loss of electron. I mean there is going to be gain of electron in the cathode. That is where reduction takes place. But in the anode there is going to be loss of electron. So when chlorine loses electron at the cathode, you're going to have chloride gas that is going to escape up. So this is the cell. We have this anode as a positive electrode, we have this cathode. So we close the cell here. This is photic source. This is molten sodium chloride. Then ion screen is there to just screen it in case of impurities. So now after chloride has lost electron here, it's going to become a gas. So gas, chloride gas can escape from here. The sodium ion going to gain electron from the anode. When it gains electron from the anode, it becomes sodium metal. But instead of this, because the temperature is elevated, 801 degrees, that is the melting point of sodium. But don't forget, this reaction takes place at 600 degrees Celsius. It means we are going to have something that will reduce the melting point of sodium chloride, because 801 is very high temperature. What we're going to add to this is calcium chloride. Don't forget, in colligative property, when you have another substance in a particular in a particular salt, there's going to be a reduction in melting point. I said it when we were talking about change of state. I said when you have an impurity in a substance, impurity doesn't mean that something is useless, but in the context to which we are using it, it's an impurity. We don't need it. So in this case, calcium chloride is an impurity. So when you have impure calcium chloride, no matter how small it is in sodium chloride, so it's going to serve as impurity, thereby reducing the melting point of sodium from 801 to 600, so that reaction can take place at 600. So in that case, this is the overall this is the reaction at the reaction at the anode. So if you sum them together, you have this overall. So chloride gas escapes, then we have sodium in liquid form because the temperature is very high. So we collect sodium metal here in form of liquid here, then we can try to use it how we are going to use it. Then, so the separation of molten sodium and chlorine prevents recombination, because if we don't separate them from this reaction, there's going to be a recombination, because sodium is highly reactive, chlorine is highly reactive. So when there's enough contact time for them, they will recombine together and form sodium chloride. So we have not done anything. So we need to separate them as early as possible to prevent recombination. Again, the liquid sodium flow to the solvent. It floats simply because of its lower density. Then the calcium chloride goes to storage tank and it is collected. I mean, sodium floats to the surface, not that it is less dense than chlorine. I mean, with respect to calcium chloride that we use to drop the boiling point, instead of the calcium chloride to escape here together with sodium, because somebody will ask, why is calcium chloride not escape with sodium? No, calcium chloride is denser than sodium metal. So sodium metal will flow, so calcium chloride will remain here. Then and of course it is gas. Chlorine gas will move to the top like this and collected as a gas. That is just the way of preparing sodium in industry. Let's go to aluminium now. Aluminium, the main source of aluminium is on bauxite. That is, I said it is oxide hydroxide of aluminium. So if you want to prepare aluminium from bauxite, the first thing is purification. How do you do that? You heat sodium hydroxide together with the bauxite. If you heat them in presence of water, you have what's called sodium aluminate. That sodium aluminate is a very highly soluble compound of sodium. When it dissolves like that in water, because in bauxite there are many impurities inside, because we are digging it from the earth crust. There are many impurities inside. Some metals are there, some other oxides are there. There are some other physical components, they are there. So if you now heat it with sodium hydroxide, it forms soluble sodium aluminate. In that case, it is simple to separate. We separate soluble substance from something that are not soluble. It is very easy to use filtration. So if you use filtration, that is just physical mixture, then all the dissolved ions, they will they will go with sodium aluminate, then undissolved one will go away. So to separate the undissolved one now, what are we going to do? We are going to treat this sodium aluminate with acid. If you treat them with acid, there's going to be precipitation of aluminum hydroxide. Aluminum hydroxide and bauxite are not the same thing. So if you treat that with aluminum hydroxide, it is simple now. So only aluminum hydroxide will now be collected as a precipitate. Others will be soluble inside. Then by decantation or by centrifugation, you can remove that. Then you collect your precipitate. After collecting your precipitate, this is not where we are going. Don't forget, we need pure aluminum. So we can just remove that from the sodium because it says it's a precipitate. Precipitate means it's not soluble. So it's going to be deposited at the bottom of the reaction container. So after that, then we have electrolysis of this. So eating that sodium that hydroxide now, we get this, that is alumina. After the alumina, we now have the electrolysis in the mixture of cryolite and calcium chloride. In this place now, we have the cryolite, we have the calcium hydroxide. So when we have this, we are going to set up our electrolytic cell. After setting up our electrolytic cell, then the reaction takes place at the cathode. Every other thing will go to this place. Only the aluminium will come to this place. Don't forget, there's no hydrogen here. So out of the all other elements that are inside, it's only aluminium that will be preferentially discharged. If aluminium discharged, so it's going to form as a solid. So aluminium will now go like this, and we collect our molten aluminum. And once again, it is in liquid form. So after collecting it in liquid form, so we can now do anything we want to do to it. This particular cell is called Occurrence cell. The cell discovered by two people, one is a student and one is a professor in Germany. So we collect oxygen at the other electrode, although we don't need them, just to mention it. So let's go to the group 2 now, that is called magnesium. We want to explain production of magnesium as a representative element of group 2. What is the main source of magnesium? It is seawater. It contains almost 0.5%. You can see 0.5% is small, but that is the most abundant way of getting magnesium. So about 5% of magnesium chloride. So how do we do that? So you add calcium hydroxide to magnesium chloride. If you add calcium hydroxide to magnesium chloride, there's going to be exchange of ion. So you have calcium chloride and magnesium hydroxide. Calcium chloride is very soluble in water, so it's going to remain in solution. The magnesium hydroxide will not be soluble. In that case, you have a precipitate. So you separate them by filtration once again. After separating them, you add acid to that magnesium hydroxide. After adding acid to it, you have magnesium chloride and water. So magnesium chloride and water, then you separate them again by filtration. Then after separating by filtration, then your magnesium chloride will now be separated using electrolysis. With electrolysis, using our carbon as the both electrode, then we are going to have magnesium forming at the cathode. As I remember something now, let me go back to sodium. In sodium, we are not using solution, although I mentioned it briefly that time, but let me re-explain it. If we were to use dilute sodium chloride, instead of sodium, we are going to get aluminum. I believe you still remember that part on electrolysis. Please, if you can't remember it, please try to revisit your electrolysis lecture. So we are using molten sodium chloride, brine, because this sodium we need, not hydrogen. If we need hydrogen, we will use dilute or concentrated sodium. We just make sure there is element of water, but in this case, because we need sodium, we don't need any other ion apart from sodium that we want to separate. That is just what I want to re-explain. So another method we can use to separate metals is called chemical reduction, although it is not every metal that can be separated by chemical reduction. This method is for moderately reactive metal, although some elements like magnesium that I just treated now can be separated by both electrolysis on magnesium. But in this case, we have explained what is electrolysis of magnesium, so we will still re-explain chemical reduction of magnesium. But chemical reduction of magnesium, chemical reduction is when you have a single element that can be prepared by both methods. So researchers or industrialists, they prefer chemical reduction because it is less expensive than electrolysis, but it's only if you cannot use chemical reduction for elements, even like lithium, like sodium, like potassium. So we use chemical reduction. Use electrolysis if you cannot use chemical reduction. But if you can use both methods, like in sodium now, they prefer to use chemical, and like in magnesium now, they prefer to use chemical reduction because it's less expensive. So that's another method of separation. So it is possible to produce potassium, rubidium, and cesium by chemical reduction. It is possible to reduce the molten chloride of these metals with sodium. Because somebody will ask that rubidium and cesium are highly reactive more than sodium. How come are we preparing sodium by electrolysis and we are preparing rubidium and potassium, rubidium, and cesium with chemical reduction when we claim that they are more reactive? Yes, it is like that, but it is because you can reduce molten chlorides of OThese with sodium metal. Sodium metal is a reactive element, so if you still react sodium with all these chlorides, with chlorides of all these elements, you are going to get all these elements. So that is why it is. So and don't forget, instead of using expensive electrolysis of rubidium chloride or cesium chloride or potassium chloride, you can just react sodium with them in a less expensive method. These metals are more reactive than sodium, fine. However, the metals formed are more volatile than sodium and can be distilled for correction, and I've explained that they are more volatile than sodium. So the removal of the metal vapor leads to a shift in equilibrium to produce more metal. Don't forget the Chatelet's principle. When you have equilibrium and something change in the system, then the system will adjust itself to annul the effect of the constraint that just happened to the system. In this case, if you prepare a metal and you have a metal vapor, so you remove the metal, then in that case equilibrium shifts to the front to shift to the product to produce more metal vapor. In that case, you maximize the production of metals. So the production of magnesium, zinc, and tin provide additional examples of chemical reduction. So let's check them one after the other. So magnesium now. This is the Pidgeon method, the Pidgeon process of magnesium. How do we do that? You heat elemental silicon at high temperature with magnesium, then there's going to be reduction of magnesium chloride into magnesium. So you can see it's simple. So the removal of magnesium vapor takes advantage of that Chatelet's principle. So continue the progress, because after this first one, you remove the sodium, then equilibrium shift to the front. You remove the magnesium, equilibrium shift to the front because it is in gas at high temperature. It is in gas. So you remove the magnesium, the equilibrium shift to the front again. You remove the magnesium. So as you are removing the magnesium gas, so equilibrium is shifting to the front, so as to get more product. For zinc, there are many ores of zinc. There are many compounds of zinc where you can get zinc. So you don't have to use all the compounds. It is anyone. In this case now we are using two examples, so you can just take one. If it is zinc sulfide, that is zinc blend, or if it is zinc carbonate, you can have it is simple. If it is zinc sulfide, just heat it with oxygen to get zinc oxide and this. If it is zinc carbonate, don't forget zinc carbonate is unstable. If you heat it, it's going to decompose to zinc oxide and CO2. So almost all are the same. What we just need is the zinc oxide. So if you have your zinc oxide, then you have your carbon. Don't forget carbon can reduce oxide of any metal. So carbon reduces the oxide and then it forms zinc vapor. The same thing will happen. So if you remove the zinc sulfate, it will run shift to the front, like we explained before. You have some element of CO. So the zinc can be distilled now. That is the boiling point of zinc is 907 degrees C. Then you recondense it to form your liquid zinc or solid zinc, as the case may be. And in this case, zinc can contain some impurities like cadmium, like iron, like lead. So if you want to get your zinc in pure form, that is, use distillation. If you distill it to a particular temperature, to let's say 613, arsenic will be removed. If you distill to 767, cadmium will be released. Then if you distill to 907, you get your zinc. Then you can leave the others like iron and lead if you don't need them. But if you need them, you distill to 1750 degrees C. So you have your lead. Anything that you have left in the system is the iron. So let's go to the for the last element we're going to treat for today. So tin oxide, that is called cassiterite. That is the largest ore of tin. So if you want to prepare tin, then you roast tin oxide. You roast cassiterite. So if you roast cassiterite, roasting means you burn it inside here. So if you roast it, then you remove the volatile oxide, something like arsenic and sulfur. So you remove them. When you remove them, you now treat that material, that zinc sulfide, that zinc oxide, and you treat it with hydrochloric acid. When you treat that, you are going to have solution of other compounds. Don't forget, zinc oxide is still not soluble. Then you remove it by filtration. So after doing that, you have to heat that purified ore. You heat that purified cassiterite now with carbon at high temperature. Don't forget, carbon can reduce it. If you have observed, you are going to see that carbon has been the element used to reduce all this metallic oxide. This is because we have said that carbon is very potent when it comes to reduction of oxide of chemicals. We talked about that last lecture. So that is how to get zinc in sodium and in solid form. So let's now go to the uses of some of the metals. So let's take sodium first. So sodium is a very common compound in sodium chloride, and don't forget, everybody knows the use of sodium chloride. So you can use it to cook food, use it to de-ice roads in winter. So when you have road that has turned to ice, you have ice road. So if you want to, after turning the ice, the roads will not be motorable, and you can reduce the melting point so that the ice will melt to become water, so that the roads will be motorable. Don't forget qualitative properties again. So if you add sodium chloride to it, there's going to be reduction in melting point. Then the ice will melt and becomes water. Then the roads will be free again. It is also used as feedstock for chemical industry. There are many industries that use sodium chloride as additives. Some food industry also use it. Then sodium carbonate is used. It's a very useful sodium salt. Don't forget in removing the hardness of water. So we have talked about uses of sodium carbonate there. So magnesium now. Duralumin is an alloy of magnesium. It contains some magnesium, contains some copper and some other elements. Magnesium is an alloy of magnesium also. If you have not heard of that name, you can try to Google it. Magnesium is an alloy It contains, I think, contains some percentage of nickel and tin. Yes, and tin. So they are alloys of magnesium. They are very, very useful, especially in aircraft design and some other things. The metal is also used in pyrotechnics, especially in producing bomb, signals, and flour. So there's a fuse for thermite in thermite reaction. Don't forget we have talked about thermite reaction last class. It is used in photographic flash bulb and is added to some rocket and missile fuel. This is used in preparation of malleable cast iron. Magnesium is very, very useful. Even some compounds of magnesium are used in medicine, like antacid, magnesium hydroxide, that is used to alleviate, or to, let me say, to cure. I don't want to use the word cure, to alleviate the effects of ulcer in ulcer patients. Aluminium. Because of the light weight of aluminium is used in transportation, like in automobile, in aircraft design, in railway cars, in marine vessels. Even so, aluminium is used in electrical equipment, like in wire now. Aluminium is very, very reactive, so it is used in wire, the overhead wire, high tension wires. You use aluminium there. So you can also use aluminium for packaging of food. There are many aluminium foils that are used. Then food and beverage containers, because of resistance to corrosion. Don't forget I said last week, our last lecture, that if you have aluminium is very, very reactive. If you want to be using it where there's going to be contact with atmosphere, then oxygen will automatically attack the aluminium. After attacking it, it's going to form protective layer of aluminum oxide that is in a process called passivation. If you have something like that, no other element or other environmental agent will be able to destroy or contaminate the aluminium. Because of the passivation, oxygen will have reduced the effect from the aluminium. That's why they call it its resistance to corrosion. So before we go, let us try to check some review of what we have done. Metals occur in the earth as silicate. This S is a typographical error. Pardon me for that. Metals occur like in form of sulfate, silicate, and carbonate. Metals are prepared by either electrolysis or chemical reduction. Those are the two major elements, apart from the just normal extraction and normal washing and other things for unreactive metals. Highly reactive metals are prepared by electrolysis, like sodium, like potassium. The chemical reduction is less expensive than electrolysis. So if you have a way of, if you can separate two, in the same, you can separate an element by those two methods, it is preferable that you choose chemical reduction because it's less expensive than electrolysis. So let's have some exercises before we go. So in the electrolysis of brine, this is UTM question 2004 type R and question 1. Electrolysis of brine, the anode is dash. Don't forget I said the anode is the two electrodes, they are inert electrodes. So in this case they use carbon. They did not use platinum, they use carbon. That is just the hint. Sodium metal is always kept under oil because of the reaction, because it can react with anything when it just get exposed to the atmosphere. That is it. When calcium oxide is heated with carbon dioxide with dash, don't forget I said carbon can reduce oxide of many metals. So that one will get your choice of the answer. Which of the following set of metals dissolve in dilute hydrochloric acid? So just little knowledge of chemistry to know which of, when you have a reaction of all this with dilute hydrochloric acid. So don't forget, some are less reactive than hydrogen, and some are not soluble. So if you look at this, only copper. Hydrogen is above copper in the electrochemical series, so hydrogen will not be able to displace copper. And again, if you have copper chloride is not soluble. So I just take one of the reasons here, it's not soluble. The other reason is a copper will not be able to displace hydrogen here. So if you look at this, it is only copper present in other options like B, C, and D. So A is the only answer that it is reasonable here. So thank you for listening. So next time we are going to preparation of metalloids. So just silicon and boron will be used as an example there. We go to transition metals and non-metals. We are going to spend quite a lot of time in this aspect of chemistry because they are very, very important and they are broad. Thank you for listening, and don't forget to share and like our videos.